Thank you for the introduction. And let me begin by thanking the organizers for inviting me and giving me the opportunity to speak here. My talk is based on joint work with Cornelia Vizman, and it's going to be about augmented nonlinear Grassmannians. So, what is a augmented nonlinear Grassmannian? So the nonlinear Grassmannian, Cornelia mentioned that before. This is a space of all closed submanifolds in a finite dimensional manifold M. And an augmented nonlinear Grassmannian is just a space of submanifolds, closed submanifolds in M that are equipped with further data. So augmented nonlinear Grassmannian is going to be a space of pairs in gamma. Gamma is the additional data on the submanifold N. So in submanifold in M and gamma is some additional data on N in a space that depends on N, in a space A of N that will depend on N. So we have a forgetful map here. And I will be more specific about these spaces A of N here. Purpose of the talk. So what do we want to do with the augmented Grassmannians? We want to use them to produce elements in the dual of a Lie algebra, pairing them with vector fields. We want a pairing that takes element in this augmented nonlinear Grassmannian and pairs it with a vector field. So suppose we have a Lie algebra of vector fields. It's the Lie algebra of a convenient Lie group of diffeomorphisms. And we want a pairing here, we want a very natural pairing. We just want to sort of contract this additional data with the vector field along N and integrate. And depending on the Lie algebra, we will be led to different kinds of data along N in order to be able to write down a natural contraction like that. The upshot is that we get an embedding of this augmented nonlinear Grassmannian in the dual of the Lie algebra G. And we want this embedding here to be G invariant, equivariant. So G is the Lie group with Lie algebra G. We want an action here on the augmented nonlinear Grassmannian, so we want this Lie group G to act here. G is supposed to act here. Oops. The sum group of diffeomorphisms, and we will assume that this is a convenient Lie group. But I don't want to be very general. We will have very concrete groups. We have very concrete groups in mind, such as the symplectic group, the Hamiltonian group, the group of volume preserving diffeomorphisms, etc. And what we would like to do, we would like to use this embedding here to put smooth structures on some of these coadjoint orbits here by putting a smooth structure on the G orbits on the augmented Grassmannian. So I would like to tell you there are different ways of putting smooth structures here, and maybe I'll show you a few examples first and then indicate how we're going to put a smooth structure here on some orbits. It's way too much to ask, to ask for a smooth structure on an arbitrary orbit. So what are the typical examples here? We could take the Lie algebra of all vector fields. what is the data we need to write down this contraction of a submanifold N? We need a section of the cotangent bundle of M, the ambient manifold, restricted to N. And then we tensorize the density bundle on N. And this is precisely the data that you can contract with the vector field along N. And then you get a density and you can integrate the density. So this is what you get, what you would like to have for A of N, if you consider the full group of diffeomorphisms or the Lie algebra. The second example I would like to mention are the Hamiltonian vector fields. Hamiltonian vector fields can be identified with smooth functions. If you're considering compactly supported Hamiltonian vector fields, and then the data you need along N is just the density. And you just contract the function corresponding to the Hamiltonian vector field and integrate it over N. That appeared in Cornelia's talk. The third example is the group of contact vector fields. So we suppose we have a contact structure in our manifold. Psi is a contact hyperplane field in Tm. And the space of contact vector fields can be identified with sections of a line bundle. And the line bundle is just the quotient bundle here. The contact hyperplane field gives you a line bundle, and sections of this line bundle are in one-to-one correspondence with contact vector fields. That's kind of similar to the identification you have in the Hamiltonian case here. Take a function, you take its differential and use the symplectic form to produce the contact vector field. And then similarly here, if you take a function of this line bundle, you apply a first-order differential operator to get your vector field. In this direction is a differential operator. The map in this direction is just zero order. And in this case, the data you want on your manifold is a section of the dual bundle of this N, so that you can, or L, so that you can contract, and then you need a density to integrate. And the last example, featured in Cornelia's talk too, take exact volume preserving, exact divergence-free vector fields on M, use a volume form. You can also think of a volume density, though that would require minor modifications in what I'm about to write down. So what do we need here? A of N, we can take the same thing as for the full diffeomorphism group. And that works if the codimension of the manifold N is at least 2. But if the codimension is 1, take a quotient here. You have to take a quotient. You have to mod out a finite dimensional subspace. And this finite dimensional subspace is just a cohomology, zeroth cohomology of N with coefficients in the orientation bundle of N. So for every orientable connected component of N, you have one-dimensional summand. You use the volume form to embed this cohomology in here. You want to mod that out because if you would pair, as indicated here, you will get 0. And you want this inclusion here to be this should be an inclusion in embedding. So if you mod that out, it's not going to be injected. So these are the examples we actually care about. And look at the A of N that appear here. It's rarely the case that the A of N only depends on the intrinsic, is only intrinsic to N. most of the time, it also depends on the way n is embedded in the ambient manifold M. You see that here clearly. You see that here and here too. That's the first point I would like to mention. And the second thing I'd like to point out is that the full group of diffeomorphisms is not going to act naturally on these spaces, usually. Of course, here the full group of diffeomorphisms acts. Here too, but here certainly not. We need a contact diffeomorphism to get an action on N that we can use to act here. So only contact diffeomorphisms will act here naturally. And here on this quotient, only volume preserving diffeomorphisms are going to act, because the embedding of this cohomology in this space here depends on the volume form.
So can you repeat the definition of chi, C, and C?
Yeah, these are exact.
No, the other one. Before.
This one.
No, before.
But these are just contact vector fields on N. Vector fields that preserve the contact structure.
Okay.
Structure
so when using psi, it's preserving the contact hyperplane.
Yeah, psi is the hyperplane.
Yes.
And these are the vector fields that preserving the hyperplane. Yeah. So in the general picture, for the definition, we say A is an augmentation functor if, well, there's three properties. First, it should assign to each n in this nonlinear Grassmannian, it should assign a space A of n, and that is assumed to be a Fresher manifold. It's certainly the case in all these examples here. And the second thing is some functoriality. If we have a diffeomorphism in our group G, we want a smooth map from AN to A EN. This is assumed to be smooth and functorial. Certainly the case in all these examples. And the third assumption we put is we ask for as much smoothness as makes sense. So we ask for, how did I put that? The GN action. AN, smooth. So GN is the isotropy group. So all G and G, that should G of N equals N. We do not assume that this is a Lie group. This is a strong condition, and in many examples, I'm not even sure if this is the case or not. We try to circumvent this condition, that this is a Lie group. And when I say the action is assumed to be smooth, I mean you look at maps into Gn that are smooth in the larger group G, and then composing the action with these maps, it's supposed to be smooth. You can speak about the smooth Gn action, even though Gn is not a Lie group. You just use this, I suppose, Fröhlicher structure that's inherited from the ambient Lie group. So then we call that an augmentation factor, and these conditions are definitely satisfied in this situation here, in these examples here. So what is the plan? How are we going to put a smooth structure on this space here? Well, we are not going to put a smooth structure on the full space. We are going to only put a smooth structure on this space over an orbit in the Grassmannian here. We're going to use the group structure G to put smooth structures on subsets here, on orbits here. And the idea is, well, we put a smooth structure, or we assume that there's a smooth structure on the orbit down here. I just assumed that the fibers are Fresher manifolds, and we're going to use the G action up here to transport this smooth structure around and put a smooth structure on subset. This is the plan. So the base, nonlinear Grassmannian, that's a nice Freshy manifold. Tangent space is just, Cornelia mentioned that the tangent space and modeling space is just sections of Tn, restricted to n mod Tn. This is a good manifold, and we say G has good orbit at n. G has good orbit at n. It's not about the augmentation yet. This is just about orbits in the nonlinear Grassmannian. A good orbit at n. Two things happen. Well, the orbit is a submanifold. Notation for the orbit I will use is this. This is just the orbit in the nonlinear Grassmannian through n, the G orbit. Subset in here. And this is assumed to be a submanifold. I'll show you examples in a minute, and these examples suggest to assume an initial submanifold. It's always, in all the examples, it's splitting. So we assume this is the orbit in the base has a smooth structure, inherits a smooth structure. It's an assumption. And we want more, to use the G action to transport the smooth structure around. We need that the G action on this orbit has local smooth sections. So local smooth sections means that the orbit map has a local right inverse at every point. There's no, yeah, so this is not automatic. That's the second requirement. At least I don't know how one could prove that one implies two in general. Let me give you two examples. Two examples that will show that the orbits in this nonlinear Grassmannian of the Hamiltonian group and the volume preserving group can be interesting and complicated. The first example concerns the Hamiltonian group. Symplectic structures, we assume M is now symplectic, and we look at the Hamiltonian group. First guess might be, well, perhaps the group acts at least locally transitively here. That's definitely not the case, because in conditions like being a symplectic submanifold is certainly preserved under the symplectic group and Hamiltonian group, or being an isotropic submanifold is certainly preserved under the action of the group. So there's definitely more than one orbit. The orbits through symplectic submanifolds are open and rather easy to understand. I'd like to focus on the orbits through isotropic submanifolds. The first observation is that the isotropic Grassmannian, so these are now all closed submanifolds of M which are isotropic with respect to the symplectic form, they form a nice submanifold in here. This can be proved using the normal form of the symplectic form near an isotropic submanifold. So the second guess might be that the Hamiltonian group is going to act locally transitively here, but it's not the case either. The Hamiltonian group, the orbits of the Hamiltonian group here provide a foliation on this submanifold that has finite codimension. Foliation has been found by Alan Weinstein, and it's called isodrastic foliation. So the G orbits give a foliation on this isotropic Grassmannian, finite codimension. The corresponding distribution can be described explicitly, that featured in Cornelia's talk too. The distribution tangent space to this orbit subspace in the tangent space here are finite codimension, and then tangent vector is in the subspace D in this isotrustic distribution, if and only if you contract it with the symplectic form and restrict it to n, then it is exact. Explicit description of the tangent space. This is called isotrustic foliation or distribution. This is due to Weinstein. But in particular, since the orbits form a foliation, the orbits are definitely initial submanifolds. So the orbits through an isotropic submanifold is going to be a nice submanifold of finite dimension in the isotropic Grassmannian, and the isotopic Grassmannian is a submanifold in the full Grassmannian, so definitely we have good orbits through or at isotropic. Again, yeah. Yeah, and if you consider more general submanifolds, you would not expect good orbits. The other class that's really good are symplectic submanifolds. It's even open orbits, but if there's some kind of mixture, it's hopeless, I'd say. So sometimes we have good orbits.
Lagrangian submanifold. The Lagrangian submanifold is.
Yeah, that's a special case.
This one or?
Yeah, Lagrangian is just the isotropic of middle dimension.
Is it an open orbit? Is it open inside of GR iso?
No, it has a different. Yeah, so it's the Lagrangian one are open. Yeah. You can fix a dimension. These are just like connected components of the Grassmannians, unions of connected components of the Grassmannian. And the second example I want to mention concerns the group of backed volume-preserving diffeomorphisms, and precisely the case where the codimension is 1. And here, here we have a foliation too. The G orbits give you a foliation on the Grassmannian, well, of this type. Let me use Cornelia's notation, the Grassmannian type S, and the codimension is supposed to be 1. And this has finite codimension. The codimension is just the Betty number here. This is just the codimension is just the dimension of this zeroth cohomology. The corresponding distribution, so the tangent space to this orbits, can be described explicitly. The tangent vector is in this distribution if and only if, well, if you contract it with the volume form and you restrict that to the submanifold n, then it's exact. It's formally very similar to Weinstein's isodrastic foliation, so we call it isodrastic foliation 2. Distribution. Oops. Maybe give an idea why this is the case. Locally and in the neighborhood of n, we may assume that M is of the form n cross R. And we may assume that the volume form is of the form nu dt, where dt is the volume form on R, and nu is the volume form on n. That's pulled back to the product. And then we can look at the map. Or we look at the chart, functions on n, and we go to the Grassmannian. And the standard chart for the Grassmannian is by taking a function here and looking at its graph. I mentioned one submanifold in M, and this is a standard chart for the smooth structure on the Grassmannian. And in this chart, if the volume form is really that nice, the levels, the orbits are level sets, linear map, linear operator, just taking integrating functions. There's a linear map, and the level sets are just the images of points. So this tells you that the distribution is really, that the orbits really form a nice foliation. Okay. So we assumed good. So in particular, I should mention that in particular we have good orbits for the group of exact volume preserving diffeomorphisms in either codimension. If the codimension is 2, this is the situation here, but since it's integrable, it follows that the orbits are good orbits. But if the codimension is higher, then the orbits are even open, and they're definitely good then too. Yeah. How many more minutes? Is it? Okay. Okay, I see. Good. So suppose G has good orbits. Good orbit in. Then you can put structure of a Freshy manifold on piece of augmented nonlinear Grassmannians sitting over the orbit through n. You have a forgetful map to this orbit, and this map is going to be a smooth smooth fiber bundle. So first statement, I repeat, there is a natural Freshy manifold structure on this space, and this map, forgetful map, will be a fiber bundle. And the second statement is the action on this space. Smooth. So I'm not going, the proof is, the idea is very simple. You just write down local trivializations for this map. And you write down the local trivializations using the local sections of the G action here and the action you have on this space. It's just a very simple formula I put down, and then you check that this is about, gives you local trivializations of the map, and then check the transition functions. And because of the smoothness assumptions we had here in 0.3, this will tell you that the transition functions are smooth. This is what you need, and you also need that the group G is a Lie group. But it's rather simple if, moreover, G has good isotropy at N. By this I mean that the isotropic group of N is a nice Lie subgroup. Then this smooth structure can be described in a different way. And this is just the associated bundle so if the isotropy is good, then we have a principal bundle. We have started with that. Then the G action principal the N bundle, the associated bundle. Smooth structure on the associated bundle is just a smooth structure. So if we have good isotropy, then it is the smooth structure you would use, but you do not have to assume good isotropy. You can put the smooth structure anyway.
Gn is a smooth subgroup.
Sorry, if moreover G has good isotropy, then this is a principal bundle.
So by good isotropy, you mean?
I mean that the isotropy group is a Lie subgroup.
Is a Lie subgroup.
Yeah.
This one.
Strong assumption, yeah. But the point, I guess part of the point of my talk is you do not have to be in this situation. You have the smooth structure on the way. Okay, so far we assumed that the orbit submanifold here is smooth, nice, it's good, and we put a smooth structure on the pre-image of this orbit. What we are actually interested in is G orbits in here, because G orbits in here via this embedding will correspond to coadjoint orbits. So we would like to make sure that the G orbits in the augmented Grassmannian are smooth. This is one more condition one has to put. If G has good orbit at N, the second condition now is that the group, the isotropy group, has good orbit at gamma. I'm only going to say in words what that means. The isotropy group acts on gamma here, so this is going to be a subset in here. We assume that this is a submanifold, again splitting an initial submanifold. This is the first condition. The second condition is this action on the orbit should have local smooth sections. And again, we do not assume that this is a Lie group, and the local smooth sections are supposed to be smooth into the larger group G. It's sufficient. If this happens, then the orbit in the augmented Grassmannian subset in the full Grassmannian, of course. This is a submanifold. Again, an initial submanifold that splitting initial submanifold. The G action is smooth this orbit. And we have a forgetful map from this orbit to the orbit to N, and this is a fiber bundle with typical fiber A of N. So this is what you want, and my point is that it's only two wild conditions. If, moreover, we are in the situation that the isotropy is good, that can be described associated bundle. We now just take the orbit gamma here. This is if good isotropy at N. And we have a different description. Again, it's a strong assumption. If that happens to be the case, then this is probably the way you would like to put a smooth structure on here. But if you don't have the strong assumption, you can proceed in this way. Okay. So maybe the proofs, all proofs here are very simple. It's just, I guess, feeling out what the right conditions are, what the right assumptions are. And then everything falls into place. The substance here is always in the examples. I will only say in words how this is related to Cornelia's talk. So Cornelia had a decoration on the submanifold. A decoration that is something that does not depend on the way N is embedded in the ambient manifold N. But certainly any decoration Cornelia had is an augmentation, or decoration functor she had can serve as an augmentation functor, like here. And then we have two smooth structures. The one smooth structure she described by taking associated bundle using the bundle of embeddings. And we can take the smooth structure I just presented here. And they are the same under reasonable assumptions, under the assumptions you would expect, and I'm not going to spell it out because of time. But these are two rather different descriptions of the smooth structure, and they coincide whenever you would expect them to coincide. I'm going to skip that, and I'm going to jump to examples. I would like to mention a simple example and a more elaborate example. We can take, of course, the full diffeomorphism group. Recall the weights, or the decoration we put sections of T star M tensor densities. So do we have good orbits? And the answer is yes. We have good orbits at any in the nonlinear Grassmannian. That just says that the diffeomorphism group acts locally transitively on the nonlinear Grassmannians. There's a little more. It says that the action has local smooth sections. Well known. And definitely the case here. So the orbits are good. The orbits are even open subsets in there. What about good orbits at the decoration, at gamma? And we cannot expect to have good orbits at any decoration, but we do have good orbits if the decoration is non-vanishing, gamma, and the gamma is a section of the annihilator of n, Tn, and so the densities. So this is a subspace here in all of An, just functionals that vanish on the tangent space of N. And we need a gamma that's nowhere vanishing in here. And through these gamma, we do have good orbits, and actually open orbits in this space. So then these two assumptions are satisfied, and we get a smooth structure on the nonlinear Grassmannian. the augmented nonlinear Grassmannian that can actually be identified. What that is, this is just your open and closed subset in the cotangent bundle of the Grassmannian. We put a regular cotangent bundle, and the X refers to nowhere vanishing augmentation. So this is a simple example, and the second example I would like to mention are contact diffeomorphisms.
Diffeomorphism group of N.
In red N.
Yeah.
This is a good isotropic group. But it's way more interesting if you look at, say, just look at volume preserving diffeomorphisms that also preserve a submanifold. So I've got dimension 1. I do not know if this is a nicely subgroup. If you look at the proof of Hamilton in this long paper on the implicit function theorem, it looks like perhaps it's going to work, but it's by no means obvious how to proceed. So let's look at the contact group. Is again a contact distribution on M, and we look at the group of contact diffeomorphisms. Recall the weights in a section of the dual bundle of this line bundle and L we get from the contact structure times densities. Here, the group of contact diffeomorphisms definitely doesn't act transitively on the nonlinear Grassmannians, just because conditions like being isotropic will be preserved under the group action, or being a contact submanifold will also be preserved. The good source, the easy to understand case is the isotropic manifolds, now isotropic in the contact sense, of course. But again, this is a nice submanifold here. Case of isotropic submanifolds. Grassmannians in all Grassmannians. The submanifold, and again, you prove that by using the normal, the normal form for the contact form along an isotropic submanifold. Using that, it's easy to see that this is a submanifold, an infinite dimensional submanifold, and the G action, the certain invariant under G. But in this case, the G action on this isotropic Grassmannian has local smooth sections. Particularly is locally transitive and infinitesimally transitive, but it even has local smooth sections. So that means that we have good orbits at isotropic again, because they're open here, and this is a nice submanifold. We cannot expect that the orbits of the augmentation will be nice in general, just as we couldn't expect it here. But there's one case where we do have nice orbits or good orbits. This is when we have nowhere vanishing weight, and the orbit through this nowhere vanishing augmentation will be open and even good. So we have good orbit, non-vanishing, or nowhere vanishing, I should say, gamma. This is it's not so easy to see, but it's a consequence of a stronger statement. Maybe let me formulate this because it's the only theorem in my talk. This is joint work with Cornelia Vizman. In the contact situation, you can look at embeddings. You can look at embeddings from fix a closed manifold S like Cornelia had, and you look at the density bundles, the line bundle over S, and you look at embeddings from this line bundle into the line bundle L over the contact manifold. And you want fiberwise linear embeddings. So this is some space that sits over the embeddings from S into M. We call that epsilon. Actually, I have to put well here. There's a moment map. The moment map that corresponds to the diff S action, and that will take you to one forms on S with values in the densities. And the theorem tells you that each level is smooth. It's a smooth submanifold. No matter what value you pick, the level is going to be a smooth submanifold. The G action on the level have local smooth sections. Put an action as you would like to have, and the isotropy. So these are all G and G that fix an element in this space epsilon. So phi is some element in this space epsilon. The isotropy group of such a phi is a Lie subgroup. I find that's quite remarkable that you do not have to put any assumptions on the level here. You always have smooth levels. You always have like good action and good isotropy group. And let me just indicate how the theorem implies this one here. You apply the theorem for the level 0. Being in the level 0 just means that this is going to be an isotropic embedding. And then you mod out the diff S action, and you get the isotropic Grassmannian. And so the smooth structure you have on the level after modding out the diff S action is going to give you the local smooth sections you have upstairs on the level after modding out the diff S action will give you local smooth sections here, because you can also split the bundle, the map from the embeddings to the Grassmannian. That can be locally split, and then you compose with local sections for over there. And yeah, maybe this is a good time to conclude my talk. So thank you for your attention.